Welcome to lesson 5 of my refresher course. Today we're going to look at trigonometry. Check once. Okay. So let's have a look. So just as a warm-up, have a look at the following and decide which ones are true and which ones are false. Just have a look to sort of jog the memory a little bit. Okay. So sine 30. Sine 30 is equal to a half. That's correct. Sine 60, so we can go over here, find this page. Sine 30 is equal to a half. Sine of cos of 60 is equal to a half, yeah, as well. Cos of 60. Tan of 45. You can kind of think about it a little bit. So, tan, here's a triangle, and here's a right angle. And if we have a 45-degree angle, then what are we saying? So we're saying the rise is equal to the run, right? And a 45-degree angle. So this side is equal to that side. So tan of 45 will be equal to, this side over this side, but that'll be equal to 1. Okay, we'll talk about this more in a minute, so that's wrong. And this one here, sine squared plus cos squared theta is equal to 2. Let's have a quick look at this. Now, when I have a look at this, so when I have a look at this picture here, I might take this over. Look at this real fast. Okay, this is a picture of the unit circle. Okay, so what does it mean by unit circle? It just means a circle that is centered here on the origin. So it's centered here on the origin, and it has a radius of 1. Okay, so if we have a point on that circle here, what do we know? Well, we know SOH-CAH-TOA. So we know that sine is the sine of the angle A is equal to the opposite. Let's call that side the opposite over the hypotenuse, which is just 1. So sine of theta is equal to, sine of A is just equal to the opposite, okay? And this is let's say this is the adjacent here. This is the adjacent here. Cos of A is equal to the adjacent over the hypotenuse, which is equal to 1. And that tells us that cos of A is equal to the adjacent. That's an over opposite. This is cos of A, and this is sine of A. So all that says, in other words, that this side here, this side, the adjacent side, in the unit circle is just the same as cos of A. And this side here, the opposite side, in the unit circle is the same as sine of A. And this is a right angled triangle, so this means that, well, this side squared plus this side squared is equal to this side squared. So, A squared plus O squared, A squared plus O squared is equal to 1 squared, or is equal to 1. But instead, that's the same as saying cos of A squared plus sine of A squared is equal to 1. And then this here is, you see that we don't like this, so we write it like this. Okay, it's just a shorter hand. We mean the cos of A all squared. We don't want to write those brackets the whole time. If we did cos of A squared like this, then we would think it's cos of A squared, you see? So we just want to have a way of writing it so we know what we're talking about. So we just put the square in between the cos and the A, and sine squared is equal to So what I'm saying with all of that is that this here is wrong, and it should be 1. Okay, and that's just Pythagoras theorem. So this is a quick warm up. So what are we doing with trigonometry? We're linking angles and sides in triangles. So not just in all triangles, not just right angle triangles. So we're going to have some, where are we? So we'll have some triangles like this that we can apply trigonometry to solve. Okay. And for right angle triangles, we're going to have, the rules as you already know, SOH-CAH-TOA, and Pythagoras. So we're going to still be able to use that one, but we're going to be able to extend trigonometry to triangles that don't have right angles. Okay. So beyond the SOH-CAH-TOA, we have the sine rule, the cosine rule, and we're also going to talk about radians. So, you can measure distance in miles and kilometers, or temperature in Celsius and Fahrenheit. So we have two different measures for angles. That's radians and degrees. You've been using degrees, all through school. Then in fifth year, you talk about radians. For the first time, we'll talk about that and what it means. And then we have finally these trigonometric identities, which we'll also talk about. Okay, great. So, okay, so let's talk quickly. We're going to review SOH-CAH-TOA and review what we mean by sine theta, cos theta, and tan theta. And then we're going to just try to work it out in a small triangle. Okay, so it's just easy to kind of get lost here. I think part of the reason lots of people don't like trigonometry because of these sort of just like longer words and stuff, right? Instead of like symbols. It's kind of weird. But all we're saying is that in a right angle triangle, right, the longest side is the hypotenuse, right? Sorry, I just need to, this thing keeps popping up. Settings. Just want to forget that keyboard that keeps popping up. There we go. Okay, so in a right angle triangle, the longest side, right, is the hypotenuse. And here we're calling, it doesn't matter, but they just call it the hypotenuse. It's just got this fancy name. So this is the longest side. This side, right, is shorter, and this side is shorter. So this fraction here, the opposite over the hypotenuse, has to be less than 1, and this one also has to be less than 1. Okay? Now, if sine of theta is like, if it's very close to 0, like imagine it's like 0.1, what we're saying is that when we draw our triangle, then, and we take the ratio of the opposite side. This is the angle. So we take the ratio of the opposite side to the hypotenuse. What we're saying basically is that this is a very sort of not a steep edge. The angle is very small, basically, right? So what I mean by this, and then the opposite will be true. Let's say sine theta is almost equal to 1. Let's say it's equal to 0.9. Then it will be a triangle which is very sort of steep, okay? So what we're saying is that, we're just going to take the ratios of the side. So we take the opposite over the hypotenuse, the adjacent over the hypotenuse, and this will sort of help us basically get an indication about the angle, right? Like whether or not it's very, very large or very small or whatever. And then for tan, then we have this ratio, which is just the opposite over the adjacent. So all sine, cos, and tan is going to be the ratios of these sides, right? And what's more is we could be talking about like a triangle that's like, let's draw a quick triangle like so. Like imagine this is our triangle here. And then let's say we could get values. So in this triangle, we could pick an angle, and we could get values for sine, cos, and tan. And then we would get those same answers again if we made it bigger. If we made it bigger again, we would get the same values for sine, cos, and tan, because we don't actually care about the lengths of the sides in a ratio. Like the rate, the like 100 over 90 is the same as 10 over 9, right? Even though those numbers are bigger or smaller, for the ratio, we don't care. So when we work out sine, cos, and tan, that's going to work. It doesn't matter how big the sides are, okay? So all we care is just the ratio of sides in a triangle, okay? That's what it is. Now, okay, so now we want to find sine, cos, and tan for of this angle theta in a 3, 4, 5 triangle. So let's just draw a triangle, and let's say that's our theta. and then this is our 3, and this is our 4, and this is our 5. And then we can write out, well, SOH-CAH-TOA, so sine then of theta is equal to 3 over 5. And then cos of theta is equal to 4 over 5. And then tan of theta is equal to 3 over 4. So another thing is that even though I say that sine theta and cos theta, that they always have to be like less than 1, they can be equal to 1. So we could say less than or equal to 1. If they were equal to 1, it would just be like not even a triangle, just like the stem or something like that, like just something like this. But tan theta, this can be greater than 1. It can be less than 1. Basically, it's just looking at this side here and this side here, and then basically putting the opposite A over B. So if A is less than B, so if it's a triangle like this, where A is less than B, where the opposite is less than the adjacent, then this is less than 1. But if it's like this, then it's A over B is greater than 1. Okay. So, yeah. Okay. So that's just a quick review of SOH-CAH-TOA. And what happens is that, most of our questions about, so when we do trigonometry in the Leaving Cert, we're going to have like kind of, say there's like kind of 4 different types of questions, like questions about triangles. Then you're going to be given an equation with like a regular equation, except with sine, cos, or tan in it, and work out what the angle is. We're going to have questions about trigonometric identities, which will show you that's that page in the tables, which have got all these rules and stuff. And then there's going to be like sort of word type problems or like 3D kind of problems, like here's a tree and here's an angle to the tree or something like that. Now, what happens is that the questions about triangles, we basically run out of right angled triangles pretty quickly. So when we look at the triangle, we have to decide first of all, we would have to say this is a trigonometry question, right? And then we would have to say, well, it's a trigonometry question about a triangle. Okay, so it's going to be of this type here, right? But then it could be does the triangle have a right angle or not? And if the triangle has a right angle, we can use these formulas here. If the triangle doesn't have a right angle, then we have to use either the sine rule or the cos rule. Okay. Now, how do we get these rules? We sort of get them from, you can derive them, you can prove them, but basically you can just take it that these are formulas that you can apply to a triangle that does not have a right angle, and it's just a way to help you get angles or sides. Right now, there'll be a question in a moment like, how do we know when to use the sine rule, and how do we know when to use the cosine rule? And what I just say about that is that the cosine rule has got more sides in it. See, the cosine rule, almost every term is a side except for one term, which isn't a side, okay? And for the sine rule, you see, if you're going to pick, like, you don't pick all 3, right? You just take 2 of them, right? It's just, you can take any 2, like A over sine A is equal to B over sine B, or you can take A over sine A is equal to C over sine C, okay? So, and notice the way we draw a triangle as well. The angle capital A is always opposite. See, the C and the B are beside the angle, so that the one that's opposite is the A. So you just have to always, the one that's opposite the B is the B, and the one that's opposite, that's important as well. So in some situations, we might be given 2 angles. And if we're given 2 angles, well, then we must use the sine rule. If we're given 2 sides and we're asked for, if we're given 3 sides and we're asked for an angle, then we would use the cosine rule. If we were given 2 sides and an angle, then, and we were asked for another angle, then we might have to use the sine rule. So what I'll say to you about this is that, the main thing that you have to do when you're doing a maths problem is diagnose what the question is actually about, right? So it's like, this is a geometry question, this is a trigonometry question, whatever, right? So you have to know what the question is about. And then you have to go down further down to the subcategory. This is a trigonometry question about triangles. And then then you go even a subcategory again. This is a trigonometry question about triangles that don't have a right angle. Okay, and then we're all the way down to, well, we must now use either the sine rule or the cosine rule. Okay. Now, if at that point you're not sure, which of the two rules to apply, well, actually, you're in a position where you could just do trial and error. Like, so you could actually try to apply one of the rules, and if it doesn't work, then it must be the other. Okay. It's better, I guess, if you get right to the right rule. But the point about diagnosis is that, you know, you need to get down to a point where you've ruled out almost all possibilities except for one or a couple, if that makes sense. And at that point, then you could just try something and see what happens. Okay, so we're going to try it with a triangle. Let's just draw this triangle now. So we've got a triangle like, let me just draw something like what we got here. Doesn't really matter, you know, but I guess if you don't get the diagram correct, then you might get a bit, you might think that you are, let me see, what have I got here? Let's say this is 60, right? Let's say that's the side A. And then that would be you might just throw yourself off if you didn't have the right B and B, and then this is like C and C, but I don't really care about that. Okay, so A is 40 degrees. Little a is 10. B is 60 degrees. And we have to find side B, so B is question mark. Okay, so I've labeled the diagram now. As soon as I've done this step here, label the diagram, 3 marks out of 10. Okay, next one. So what am I after? I'm after B. Now I could actually write this as sine A over A is equal to sine B over B. It's just exactly the same thing. You just flip both sides. What you can do, what you can do is if you're asked for an angle, you would use this form. If you're asked for a side, you would use this form. I'm going to pick out from this what I need. A over sine A is equal to B over sine B. Now what I'm going to do is I'm going to fill in A over sine A. 10 over sine of 40 is equal to B over sine of 60. And then we're going to say 10 times sine 60 over sine 40. That's equal to B. I usually just sort of leave it here. We're now definitely at the 7 over 10 level. 7 out of 10 level. And now to work that out, we'd have to, sub in the values, like use the calculator and so on to work that out. And I'm just going to leave that there to give us more time. Now, there is one case that's actually kind of interesting. It's actually kind of ambiguous. So let's have a look at this for a second. We have a triangle. Let's draw it. Like with a 40-degree angle. And this is my B here, and that's my A here. And I have the following situation. So this is my A, and then so this is my angle 40 has been put in. My side B is equal to 8 has been put in. Okay, so this would be, the angle B would be over here, right? So what's ambiguous about this? Well, the side A has to be equal to 6. And the point is that, so we have to imagine a pencil or something of length 6 or something like that. We have to be able to start that there and then land it on this line here. So we could do that one, but also that one works. Maybe I did it wrong. The way to do it is to draw a circle. So let me draw a circle. There we go. Imagine that's a circle of radius 6. You see, there's two possible this is the ambiguous case. This is a side of length 6, and this is a side of length 6. So this is just a special thing to be aware of when you're using the sine rule, that when you're given it in this way, which is the side angle way, that there's actually two ways that it can be. So we would get, in this smaller triangle, we have that angle, and we have this angle, and we have this side, and they are all different to that side, that angle, and this angle. Okay. So we have two different triangles arise for that reason. Okay, so now using the cosine rule. So as I said, like the cosine rule formula, it's actually kind of funny because it's actually Pythagoras theorem, and it's got this extra correction. That's what happens a lot of times with formulas. Like you have a standard normal formula, but it doesn't work all the time. So you add a kind of a modification. And what is this modification doing? Well, if we have our right angle triangle, see, we've got c squared is equal to a squared plus b squared for our right angle triangle. But for our triangle that doesn't have a right angle in it, then basically we need to, where is it? We need to, this extra piece accounts for the fact that it's not got a right angle in it. Okay, so we can derive it. We're not going to, I don't think you do it on Leibniz here, but it's not that crazy a derivation. It's just when you go and you try to work it out, then you'll find that you're left over with this extra term here. And we're going to use this for, if we don't have right angle triangle, and then if we're given three sides and the question is to find an angle. Okay, so just practicing a few of these will allow you to be able to differentiate the cases, like when do you use the sine rule, when do you use the cosine rule, and if it happens that you were to apply the wrong one, then it's not the end of the world. Okay, so an example of the cosine rule. So what I'm going to do before I do anything is just usually what I do is I just gather what I need. So let me just get this here. So I need this thing. And as well as that, I also want to see how it's being applied as well. Just sort of gather together the tools that you're going to need, put them right beside you. Like this. Okay. And in our case here, maybe it'll work. Won't really work, will it? But it doesn't really matter. Like I'm just going to say this is 5, this is 7, and this is 10. And then we're looking for this angle here. Now I know that doesn't really make sense, right? Because this is clearly the longest side, and that should be the shortest side, and things like that. It doesn't really matter. Like when you're doing these, you're not getting judged on the quality of your diagram. Your diagram is only supposed to sort of just to lay things out a little bit, just ready for the formula. You wouldn't get marked down or anything for that. So now we're looking for the cos of C. And the most important thing when you go to do, see, this is the mysterious thing, okay? The thing that we're after. But this is what the question is about, right? Now, what we've got to do is we have to make this sort of axis across the triangle. Right? We have to link this like here, right? And we have to realize that in our cosine formula, that our cosine formula is bookended. I hope you know that phrase. It just means, if you have a books on a bookshelf, you have these two weights at either end, right? It's bookended by the side is on one side and the angle is on the other side. Doesn't matter about the other ones here. Like if you mix them up, it doesn't matter. This bit is like, so this is now, we're doing this question and we went and we labeled this sort of stuff. This is like enough for 3 marks out of 10. Okay, but now let's have a look at the next stage. So I have C is 10. So 10 squared is equal to A squared, 5 squared, plus B squared, 7 squared, minus 2 times 5 times 7 times cos of C. Now, if we didn't do that right now, having done that right, we're at 7 marks out of 10. And there can be like wisdom here in saying, you know what, 7 marks out of 10 for 45 seconds of effort is pretty good. I'm going to save myself the rest of the 5 minutes or so it's going to make me to do this question. Right, that because you might be like, I only need to get such and such mark or something, right? So that it's just being sort of strategic. But so if we get to this point here, then we're going to get the 7 marks out of 10s. But if we were to make a mistake here or something, we're not going to get that. So get to the high threshold really does mean not only picking the right formula, but subbing everything into the formula and doing that correctly. Okay, so you can't get there basically unless you might get 5 marks out of 10. or something, but you can't get up to the high partial. Okay? Your aim should be really to kind of get to the high partial as quickly as possible, right? If that's really your aim, then if you can do that in like, a minute or two per question, then you're flying. You're doing awesome. Okay. Okay, now we're after cos c, so we have to get cos c in its own on one side. You may have seen this before, where cos c is actually written as c squared minus a squared minus b squared all over like minus 2ab or something like that. So that's just sort of taking this formula and sorting it out. So we have 100 is equal to 25, like plus 49, and then minus 2 times 5 times 7 is minus 70, minus 70 times cos of c. And then this is going to be, this is 74, so this is 26 is equal to minus 70 times cos of c. So it tells us that sorry, that's a, what did I do wrong here? It's 2ab 5, 7, 10. Maybe this example is wrong. I'm just going to finish this one here. I think maybe the sign is wrong or something like that. But unless I've done something, 5 squared plus 25 squared, going across, it shouldn't. It's probably I chose the wrong numbers or something when I was coming up with this example. Okay, so the next thing I want to talk about is this table here, right? And also, basically, this is about the calculator essentially, because we like these values. Okay, we like all of these values. Okay, we don't really want to put this into a calculator and then like divide it by 2 and get some decimal number and then round it off, because this is actually far, far more accurate. It doesn't maybe look like it, and I think the instinct sometimes can be to, but as I say anyway, that tan of 30, find tan of 30 exactly. I think I can do this later. The instinct is sort of like writing something in surd form is not like neat or correct or something like that. Actually, this is far better to write things like the square root of 3 over 2 and 1 over 2. And then so this is what we mean by it being exact, okay? The square root of 3, if we were to write it down, it's an irrational number, so it's decimals that go on like forever, right? Okay. Now, the next thing we're going to talk about is radian measure. Okay, so we have like, miles and kilometers, we have degrees Celsius and degrees Fahrenheit and stuff of this. And then we have like, for a circle, we have like, let's start pointing in this direction and let's turn and let's get an angle. And now let's get a measure of the angle. And for kind of like there's sort of examples where people just do things for a kind of a reason historically, and then we just sort of keep doing it that way, right? And one of those things is this idea of basically of the number sort of 6 or 60 or 360, and it's going back into history that the sort of where we get our angles from is that basically someone took the circle and divide it into 360 parts, right? Which is basically kind of arbitrary. Like, why not 100 parts, right? Or something like this. So, but we have this new measure called radians, right? And it's a much more organic way of measuring angles. So if we write down, here's a circle, okay? And let me get a proper circle. So we draw a circle. Here we go. And I'm going to get somewhere. So I get start off like this direction with my. Now I'm going to make So this circle's got a radius of r. Now I'm going to make another radius. I'm going to make an angle. So obviously this one would also be a radius of r. But this angle here is going to give me an arc length of r. Now you might be like, how do I measure an arc length? Now you can measure the radius with a straight edge, so ruler. To measure the arc length, what you need to do is you need to get a thread, and you have to get a bunch of thumbtacks, and you have to take the thread and stick it on, and then when you've got it perfectly overlapping the length of the arc, you take it off and you put that piece of thread against a ruler. So it is possible to measure arc length. It just takes longer, okay, than doing this thing here. So arc length, we can have a length, it's like the length, you can imagine that's like whatever, it's a 1 kilometer walk from your house to the shop, but the street is not straight, right? So it's just sort of like, you don't have to, like, distance does not have to be measured along a straight line, right? So we can have a measure here. So this arc length here can be equal to r. And we're going to say that theta is the angle that gives. Now, how are we going to do it? Basically, what we know is a couple of things. We know that the circumference of a circle is 2 pi r. Okay. And then we also know that 360 degrees is in the circumference of the circle. Okay, so what we're going to say is that I'll just come back to that, I think, in a moment. So like this would be 1 radian. This is 1 radian, and it's about 57 degrees. Like I think of it as around 60 degrees. This would be 2 radians. 2 radians here would give us an arc length of 2r. 3 radians would give us an arc length of like 3r, right? And 2 pi r is the circumference of the circle. And so what you're noticing here is that the number of radians is always see that there, that coefficient. So 1 radian gives you an arc length of r. 2 radians gives you an arc length of 2r. 3 radians give you an arc length of 3r. To get an arc length of the circumference of the circle is the full circle, 2 pi r, you need 2 pi radians. So 360 degrees is equal to 2 pi radians. So this is our conversion now. So for miles and kilometers, I believe it's 5/8 of a mile is equal to 1 kilometer. Pounds or dollars and euro, or pounds and euro, or whatever. You have to look at any given day. You have to like go onto a website and find what the exchange rate is. Fahrenheit and degrees is like 32 plus 7 over 30. I can't even remember, something like this, or 13 over 7 or something like that. So you have this way to convert between units. So our way to convert between units is 360 degrees is equal to 2 pi. And what that tells us is basically like, if your angle is in radians, so if theta is in radians, first of all, you have to divide by the pi, and you have to multiply by 180. Or the way I actually used to do it was divide by 2 pi and then multiply by 360. That's how you go from radians to degrees. And then if you want to go from degrees to radians, you go back the same way. Now, why do we want to introduce at this late stage, like, why do we care about like introducing a new measure? Why are we making this conversion at this stage? And the reason is that basically that we are connecting something like an angle, which is a measure of how much you're turning, and also a measure of distance, right? So it's essentially, it means that you can have something like x plus like cos x in a sense, and for that to make sense, because because they both kind of relate to distance, right? So you're not kind of mixing units and things like that. This is like one way to think about it. So it's just it just works better, and most of the time we're actually going to use like radians. Almost, let's say, we kind of start to use radians, but then if you were to continue studying maths, then you'd basically just like always use radians, right? Okay, great. And so, yeah, we have this formula. The arc length formula is L is the arc length, is what I said. The arc length is equal to r times theta, where theta is in radians. Okay, so this arc length L, you have to work out the number of radians, which might be 1 radian, which is 57 degrees, right? Around, like, what I think about it is like you have like a pizza, and you split it into 6 slices. And each of those 6 slices is like a radian, something like that. You know, instead of 360, it's not 6 because it's 57.3, so it's almost 6, right? But it's pretty close to 6, right? And 2 pi is, well, pi is almost 3, so 2 pi is almost 6. Okay, so that's, it's just a way to kind of give yourself an intuitive concept of what a radian is. It's not even, it doesn't fit in evenly because of this aspect that we are actually, we don't really care about our angles fitting neatly into the circle. We're not dividing the circle neatly into 360 parts or something like that. We care more about like the connecting the angle to that length there. We care more about that arc there. So we're going to find, okay, so we have a question here. So we have a circle which has a radius equal to 6. So I don't know, maybe it's just me, but I always find if I'm given a question, I look at it, I just see weird text. As soon as I kind of write it for myself below, I'm kind of like, you know, theta is equal to 150. I can kind of see my way to the solution. And now we're looking for the arc length. So the arc length is equal to, you know, or theta. So I'm going to say or times, what was it, 6 times, and I'm almost about to make a mistake, but see, I can't use, so I have to convert, okay? So I have to say that theta in radians is now equal to, so what you're doing is you're sort of like taking the angle, you know, divide out the angles, and then multiply by pi to give us the, now this is the way that we're going to convert, okay? And because basically 360, it's just like anything. If you, those old questions that you did about 360 degrees and so 360 degrees is equal to 2 pi radians. So this is how, or 180 degrees is equal to pi radians. Okay, so that's how you do the conversion. Now, the other thing that we have is sector area. Okay, so you can get the area of a sector. Basically, we have like pi r squared is the area of a circle. And what we have then is instead of the r squared, we have a half theta, where theta then is in radians, right? So this is anyway how we can actually then, so this we have a formula for arc length or theta, so we can get that one-dimensional thing, and then we can also get a two-dimensional thing as well. So that's the this area formula here, area of the sector. And let's say we have r is equal to 10, and then theta is equal to 1.2 radians, which is about, what is that? A radian is about 60. So 0.2 of a radian is probably about, whatever, 15 degrees. So it's about 75 degrees, something like that. I don't know. And what I'm doing there is, it's called back of the envelope calculations, right? So you're sort of like, you're a lot of the time, like you're able to kind of, without doing any calculations, at least get into the ballpark of what your answer should be. You know, you don't have to do that, but it can kind of contain the question in a way, like okay. And then if we want to work out what the area then is, then it's a half r squared theta, which is a half times 100 times 1.2, and that ends up giving us 60. Okay, so now let's talk about trigonometric identities really quickly. 1 second. Now, trigonometric identities were, it was basically something that really kind of confused me when I was leaving certain stuff. Like this page here, sort of thing. You know, I guess my attitude, like this stuff and this stuff, and it was sort of like, it wasn't that I didn't like know how to do them. I was just like, why are we doing all this? Like, what do we, like, what's the point? Like, I have a calculator, right? Like, why do I need to do all of this stuff? And the point about it is, which they don't really emphasize enough, in my opinion, is that, let's say, for example, you have that sine of A is equal to 0.3. And you've got sine of B is equal to 0.7 or something. Okay, let me make it 0.6, right? Just two things. Well, what we're going to be able to do is we're going to be able to get sine of A plus B, sine of A minus B, we're also going to be able to get cos of A. Then we'll be able to get like cos of A, cos of B. Then we'll be able to get cos of A, cos of A plus B. We'll be able to get cos of A minus B, then tan of A, then sine of 2A. So what we're saying is that we actually only we once we've done it once or twice, once we've got a couple of these things, these are like sort of seeds, and we can use them to get like the sine of all these other angles, right? So, and it kind of happens like, you know, it would make sense that, like, let's say, for example, you might be in some sort of construction project or something like that. Like if you, I don't know, sometimes I think about the inside of the Stevens Green Shopping Center, but if you look from the top deck, you can kind of see all these sort of arches, and then you see all these sort of like scaffold, and you see some that are like are pointing like this, and then others that are pointing like that, and then other ones that are point like this, you know. So what you have is like maybe an angle, but then double that angle, and then that one goes to the, you know. So you have this whole way in which everything's kind of regular, and you know, and so for this reason, it just happens that like we kind of like once we have the sine of A, and once we have the sine, once we have like cos A, sine A, and tan, like a couple of examples, then we can kind of go and get we can get other things from that, right? So, for example, tan A is sine A over cos A. Why is that? Well, let's go back to here. So, um, tan A is sine A over cos A. So this is tan A, which is A over B. Sine A over cos A would be A over C over B over C. And the C's would cancel, so you'd just be left with A over B. Okay. So this is one we use a lot. This is one we use a lot as well, which I also showed you. These ones we can talk about. These are that's just because they reflect in the axis. So this is cos of A, which is the horizontal side, and then minus A would be going down. So you'd have the same sides of triangles touching each other, which is why that one would be true. You know, you see down here, this is A plus B. So if we had cos of A and cos of B, then we could get sine of A, and we could get sine of B from this formula above. And then we could get cos of A plus B, cos of A minus B, the same for sine of A plus B, and then we could get the tans, and we could work out. So this gives us a kind of a way to kind of like, you know, we haven't just worked out sine and cos of one angle, we've worked it out for a whole load of other stuff. Now in leaving cert, you're given a few of these to prove. And let's say, for example, if you had to prove this one here, the rule is that you're able to use any of the others. So so what we would do is we would take probably for tan of A plus B, we would realize that tan A is sine A over cos. And so if we were looking to prove this, we would probably take like sine of A plus B over cos of A plus B. So we can just take those two above, and then we can do some bit of algebra, manipulate things around, and we'll end up with this. Okay. So anyway, so just long story short, we have these we basically have these two. Once we work out sine and cos or something, then we can get all of this other stuff. And this is the way that we would get that. Okay. That's fine. Let's move on. So sine squared plus cos squared is equal to tan theta is equal to sine theta over cos theta. Then they've got sec theta is 1 over cos theta, and then cosec theta is 1. So we just also have these other, they're called reciprocals when they're, it's 1 over something. So it's not a new thing. It's just when we have 1 over that, we're not going to write this. We kind of like, if I'm going around like writing 1 over cos theta, it's just annoying. So I'm saying, you know what, I'm going to give this a new name, and I'm going to call this sec of theta. You know, it's just always you're finding a shorter way to say things, basically. And it looks like, you know, something very sort of complicated. Then we have this one, the double angle formula, sine 2 theta is 2 sine theta cos theta, cos 2. So if we had sine theta, then we could get sine 2 theta, right? So if we had sine of 15, we could get sine of 30. If we had sine of 30, we could get sine of 60, right? If we had, and the same for cos, right? And then, yeah, so then we have, this is actually kind of worth doing. So we have a question which is sort of saying, write down cos of 2 theta, but write it not with a cos squared theta and a sine squared theta. Write it in terms of cos squared theta only. Okay, so cos 2 theta is equal to cos squared theta minus sine squared theta. And we want it in terms of cos squared theta only. So we need to get rid of that thing. So we have to go back, like, how could we get rid of that thing? So I need to find a formula which has got a cos squared and a sine squared in it and nothing else. And that's this one. So I take that across. You see what you're doing? It's like you're cooking, you know? It's like you're like, okay, now I have that thing. Now I'm going to put it together with this thing and I get a new thing, you know. So that means that sine squared theta is equal to 1 minus cos squared theta. Okay. And then I have cos squared theta. And then, you know, I try to jump a step and I say, okay, that's cos squared theta minus 1 and minus cos squared theta. So then the cos squared theta is cancel and I'm left with a 1 or something. And it's all because we jumped a step and we just didn't use a bracket because we were trying to save time. But then in reality, how much time did we actually save? So it's cos squared theta minus 1. And then it's minus minus plus cos squared theta 2 cos squared theta minus 1. So that's a way to write cos of 2 theta only with cos squared theta. Brilliant. Okay. And then we have an example, a worked example to take something like this, like 1 minus cos 2 theta divided by 2. And we want to simplify this. So yeah, so they end up doing stuff like this. It's kind of annoying, but it's quite predictable also in a way. So first of all, we want to say that cos of 2 theta. If we go over to the tables, I believe the cost of 2 theta somewhere. One minus cos 2 theta. So they can write it as 1 minus 2 sine squared theta. I'm not too sure what's didn't we just write this as in terms cos 2 theta was 2 cos squared theta? Yeah, I think this is a mistake. So we just worked this out on the previous page. So this is now equal to, sorry. Um, so this is now equal to, what was it? 1 minus, and what was our answer for cos squared theta? 2 cos squared theta minus 1. Just forget that. I don't know how I put that in. Uh, that's a cos, and then that's all over 2. And then we have um, this will be 1, this will be 2 minus 2 cos squared theta all over 2, and then it's like 1 minus cos squared theta. There's an awful lot of this stuff is dedicated to just sort of playing around with these things, see if we can get from one to the other, you know? And you kind of might think it's useless, but um, and why do they dedicate so much time to it and stuff like this? But I think what's nice about it is it just demonstrates, and maths happens all the time. You find one or two or three things, you make one or two or three assumption, and it really balloons out. All of a sudden, you have pages and pages of all these sort of things that you can derive from that. So think about like a tree that goes up, it doesn't have like one, two, three branches at every branch. It's got like 100 or something. So maths is really this sort of like this big logical structure like that goes off like crazy, right? So many things are possible from it. Okay, so we just have some other stuff, and I have a little quiz here. So okay, so just maybe take a moment just to have a look. The first one is to apply the sine rule. The second one is to apply the cosine rule. The next one to convert 225 degrees to radians. And then the next one is to work out the arc length. And the final one is to simplify cos squared theta plus sine squared theta. Yeah, I think simplify. I guess it's just equal to 1, right? So maybe how about take a few moments to have a look at them. I'll start writing some stuff down. So you'll see the first thing that I did was I just copied out the sine A over A is equal to sine B over B, but we've been asked for B. So this is wrong. I should have written just the other alternative form of the equation. A over sine A is equal to B over sine B. So this tells us that 8 over sine 40 is equal to B over sine 70. Okay, let's just leave it there. That we just bring the sine 70 up. At this point, we're at the 7 out of 10 mark. And so when I'm saying leave it there, that's I often say that because I'm like, okay, now we just have to finish it off. Now everything tricky has been overcome, and now we just have to be disciplined and methodical. And you don't want to watch me being like a robot solving problems, I guess, right? So, okay, the next one is like a squared is equal to b squared plus c squared minus 2bc cos of a. And here's me just going straight to my memory and writing out a version of the formula, which doesn't quite fit here. Let me do this again, and let's have a look at what we're after. Okay, we're after c. So what I'm going to do is write the c squared is equal to a squared plus b squared minus 2bc cos of c version of the formula. So I can bookend it with b squared on the left side and capital B on the right side. I can bookend whatever I want to, and then it would just change the ones in the middle, right? So in this, sorry, look, I even made a mistake again. Here we go. This is how you do it. This is not 2bc, it's 2ab. It's fine to, like sort of this, you can see the leakage. It's like this is where the mistakes kind of creep in when you're not really paying attention. Okay, so we're looking for c. So c squared is now equal to 7 squared plus 40, no, plus 9 squared minus 2 times 7 times 9 times cos of 120. So now we're at the 7 out of 10 mark. I would kind of move on. I mean, if you want, that's something you can go through past exam papers and you can look at the marking scheme, and then you can just be like, how do I get as quickly as possible to the high partial 7 out of 10 grade, just move on, right? Because in that way you can get to the point that you're reliably getting 70% in the exam, right? Or 60 to 70% in the exam, right? Which is a fantastic place to be as setting a threshold. I mean, that's brilliant, right? And that's a great launch pad. And then everything after that point is just being really precise. That's what really filters the people who get the top grades, is just the precision. And, you can see it when people are doing their exams. You can just see basically some people are just, they're just a lot more precise in how they do it. And then they just get, most of the time people are just making mistakes with minus signs or something, Okay, so 225 degrees to radians. Okay, so I'm gonna divide 225 divided by 180 multiplied by pi, or divided by 360 multiplied by 2 pi. Arc length formula, L is equal to or theta. So that means that L is equal to or, which is 12 times pi over 3, and it's equal to 4 pi. Like maybe I didn't make this point well earlier on. L is equal to or theta. You see, L is a length, and the length here is 4 pi, you see? But pi is also an angle, you see? So the pi thing, the angle, can also be a length, you see? So we have this bridge between lengths and angles, okay? That's why radians are good. That's it. Like, there's no mystery, okay? Cos squared, sine squared is equal to, add them, is equal to 1. Great. Okay, so just a moment to look at an exam question here. So we have the field, we have these sides here. We want to find the area of the field. There was a formula that I didn't mention here, but the area is equal to half AB sine C. I'm going to go in and label everything. This is C, this is A, this is B. I know I probably haven't done that with the, but we're not going to let that phrase, we're not going to let the tail wag the dog, right? We have some sort of, if we have a picture or something that comes out of a formula book, this is just a tool for us, right, to kind of get to it. But if we're like, okay, I'm just going to throw in these labels, okay, and I'm just going to apply them, then we don't need to be. So half times 59 times 47, and then sine 28. And it says, okay, so we multiply all this stuff out, and then it says to the near, this is the filter for like, so 7 out of 10, you work this is already 7 out of 10, right? Now, to get to the top mark, after you multiply this thing out, you have to look back and you have to say, oh, I got like whatever, 100.5729 or something like that. But it said correct to the nearest meter, and it said in meters squared, right? You just have to do it, right? So if you want to get to that top level, you're going to have to look back at the question. And then it says work out the length of this side, the side BC. So let's go ahead and call the side BC. We'll call that C. And now we have the formula. C squared is equal to A squared plus B squared minus 2BC cos of C. Okay. Okay, I'm going to finish there. What I'm going to do today, I'm going to send you another email. I hope you're getting these emails. I send you these emails with some homeworks and things like this, and also with a link to where you can watch the video. So you can just, this video that I send you, you can feel free to share that with people if you think it will be useful for them. I'm also going to share a link to a review page on, I'm trying to start up a grinds teaching business. Part of the reason I'm doing this, these grinds now, just to sort of like let people know more about my grinds and stuff. So what I'll do is I'll send you a link, and if you can leave me a review, you know, that will go a long way to you know, to kind of getting more people to find me and stuff like that, you know. Okay, so yeah, so that was I think that went well. That was good. So then I'll see you then on Monday. We'll continue on Monday, and I'll be in touch before that. So have a nice weekend and good week.